Question 4 is a question about enthalpy changes. State the meaning of the term enthalpy change as applied to a chemical reaction. Enthalpy change is a heat energy change at constant pressure. Heat energy change at constant pressure. (4.2) Student determines enthalpy change. Student follows this method. Experiment how the experimental method used to apparatus can be improved, and describe how this data from the improved method can be used to determine accurate value for temperature change. 6 marks. So it's going to have 3 stages. Remember, 6 marks. It's going to be 3 stages, and we just look at the method. We're using a measuring cylinder. There's no mention of polystyrene cup, no mention of insulation, no mention of using a burette instead of a measuring cylinder or pipette, no powdered solid. Solid should be better to be powdered to give a more accurate data. So that's what we're going to do really, is what improvements could be made to the apparatus for stage 1, apparatus to provide more accurate data. Well, first things first, we want to use a burette / pipette instead of a measuring cylinder. It's not very accurate using a measuring cylinder. We also, like I said before, use a polystyrene cup instead of a beaker. Or you could say insulate the beaker, but using a polystyrene cup instead of beaker is probably preferred. You can also reweigh the watch glass after adding the solid, so we get a general idea of the value. Reweighing the watch glass after adding solid, and also using powdered solid. Stage 2. Well, we're going to experiment methods to improve accurate data. So we're going to talk about temperature measurements now. So we want to measure and record the initial temperature of the solution for a few minutes. Measure and record the initial temperature of the solution for a few minutes before addition. We also want to measure and record the temperature after the addition at regular intervals. How long? 8+ minutes, 10+ minutes, but I would like to say until a trend has been observed. That's the key point, right? You want to see trend temperature measurements. So until a trend has been observed, and then stage 3. Temperature determination. Then it says describe as data from the improved method can be used to determine an accurate value for the temperature change. Well, what we want to do is we want to plot a graph of temperature against time. We want to extrapolate to the point of addition, because this will give us the accurate temperature change, and then we want to determine delta T at the point of addition, change in temperature. That's 4.2, and then 4.3 and 4.4. 4.3. In a different experiment, 50 centimeters cubed of 0.50 or moles per dm minus cubed of aqueous hydrochloric acid are reacted with 50 centimeters cubed of 0.5 moles per DM cube aqueous sodium hydroxide. Delta H is negative 57.1 kilojoules per mole to power minus 1. Calculate the maximum temperature, calculate the maximum final temperature of reaction mixture. Assume that the specific heat capacity of the reaction mixture is C equals 4.8 joules K to power minus 1 G to power minus 1, and assume that the density of the reaction mixture is 1 gram per centimeter cubed. This is going to be really important later on, but for right now, not so much. So we want to find the maximum final temperature of the reaction mixture. So what equations do we have for this specific kind of topic? We've got Q equals MC delta T. We've got delta H equals Q over moles. We have delta T equals Q over MC. We just rearrange it. And what are we trying to find? We're trying to find delta T. That's what we're trying to find. Now it is 5 marks, so it's not going to be that as simple as substituting a value in. You should know that by now. If it's 5 marks, if it's 1 mark, 2 marks, even 3, maybe just change a couple of tricky units. But if it's 5 marks, it's not going to be that simple. So what do we know? Well, we know the initial temperature of each solution is this. Okay. So, and we also know the density of the reaction mixture is 1 gram per centimeters minus cubed. So what we should do is find out the moles, right? Find out the moles. And the thing is, it doesn't matter if we find out the moles of aqueous hydrochloric acid or aqueous sodium hydroxide. This is going to be the same because same concentration and same volumes. So let's do that. Find out the moles of NaOH. And they're both 1 to 1 mole ratio, so it doesn't really matter. Moles of NaOH. Well, it's going to be concentration times by volume. And obviously we want the centimeters cubed or mole per DM minus cube, that's why I'm divided by 1000. What would that give me? No 0.025 moles. Now I know Q is delta H times by moles. Yeah, if I rearrange this, because I know delta H is Q over moles, Q is equal to delta H times by moles. That will give me Q, and therefore we can find out delta T, Q over MC, and the mass of what exactly? Well, it's just going to be the mass of 50 plus 50, and we know it's 1 gram per centimeter cubed. Okay, so we're getting similar. So what's delta H? Delta H minus 57.1. So Q equals minus 57.1 times by moles, right? But it's going to be minus delta H. We need a positive value. Delta H is equal to Q divided by moles. Q is equal to minus delta H times by moles. It's going to be 57.1 times by 0.025. Think about if Q is negative, the heat energy released is negative, so we're not releasing any energy. It needs to be positive. So Q is going to be 57.1 times by 0.025, 1.4275, 1.4275, and this is in kilojoules, not joules, because delta H was in kilojoules per mole to power minus 1, and moles we calculated using mass or concentration times by volume in the correct unit. So it's going to be Q is 1.4275 kilojoules. Now we want to find delta T. Delta T equals Q and we want it in degrees Celsius. If we wanted it in Kelvin, then we would keep Q as in kilojoules, but we want it in degrees Celsius, so it's going to be 1.4275 times by 10 to the power 3 times by 1000 is that's Q over MC. Now the C part, 4.18. What is going to be the mass? Well, again, why would they say assume that the density of reaction mixture is 1 gram per centimeter mass cubed? It's because we're going to need it later on. That's why they gave it us in the question. So what is it going to be? Well, it's going to be the total volume of solutions is gram per centimeter minus cubed. So we've got 50 centimeters cubed reacted with another 50 centimeters cubed, which is 100 centimeters cubed, and we know 1 gram is equal to 1 centimeter cubed. So the 100 centimeters cubed is going to be 100 grams, which is the mass of the water. 100 grams. So 100. And now we can do 1.4275 times by 10 to the power 3 divided by 100 times by 4.18, and that will give me 3.42. Delta T equals 3.42 degrees Celsius. Now what is delta T? Delta T is the change in temperature. Higher temperature minus the lower temperature, the final temperature minus the initial temperature. If we know delta T is 3.42, the change in temperature, and we know the final temperature is going to be higher than the initial temperature, all we're going to do now is going to do 18.5 plus 3.42. So we're just going to add it to the initial temperature. 18.5 plus 3.42, and I get 21.9 degrees Celsius. And then 4.4 suggests how, without changing the apparatus, the experiment could be improved to reduce the potential uncertainty in temperature change. Usually when it asks about reducing the percentage of uncertainty without changing the apparatus, usually increase the mass of the solids, but in this case we're working with solutions, so it's going to be increase, not the mass, increase the concentration of the solutions. Increase the concentration of the solutions, and that is the end of question 4.